ફર્સ્ટ એક્ઝામ્પલ છે એ જુઓ. ફાઇન્ડ ધ ઇનવર્સ ઓફ મેટ્રિક્સ 1 2 3 0 2 4 0 0 5. So first we denote this matrix by A. So let A equal to 3 by 3 matrix 1 2 3 0 2 4 0 0 5. Now we know for matrix its inverse formula for inverse is A inverse equal to adjoint A upon determinant A. So denominator should not be 0. So first we have to verify the condition of existence of the inverse. So for that purpose we evaluate determinant A. Value of the determinant A, determinant 1 2 3 0 2 4 0 0 5. Now when you evaluate this determinant, its value is 10. Simple expansion of the determinant. Value is 10, which is not equal to 0, and since determinant A not equal to 0, so A inverse exists. Now we will find adjoint A. To find adjoint A, we know how to find adjoint A. So to find adjoint A, in the matrix A, each entry is replaced by their cofactors, and then that means matrix formed by the elements of the cofactor, then we have to take transpose. So first let us evaluate cofactor Aij, and we are familiar with formula of Aij, minus 1 raised to I plus j into Mij. For minor you give sign, so let us evaluate A11, A12, A13. A11 that is 10, so it is cofactor of, in the matrix it is cofactor of 1. So you leave the column and row in which that element lies. Remaining elements will form 2 by 2 determinants. 5 into 2 10 minus 4 10, and we will give sign plus. Either you give sign according to plus minus plus, minus plus minus, plus minus plus, or you give sign according to minus 1 raised to I plus j. It is one of the same. So A11 is 10, A12 it is cofactor of 2. Now cofactor of 2, so again you leave the column and row in which that entry lies. Remaining will form 2 by 2 determinant 0 4 0 5, value is 0, so A12 is 0. Similarly A13 it is cofactor of 3, so again you leave the column and row in which that entry lies. Remaining entry will form 2 by 2 determinants and its value is 0, so A13 is 0. Similarly A21, so it is cofactor of this 0, so again you leave the column and row in which that entry lies. Determinant 2 by 2 determinant formed by the remaining entries 2 3 0 5, so its value is 10. Value is cofactor, it is 10, and we will give sign minus, so A21 it is minus 10. 5 into 2 10 minus 0, and minus 1 raised to, since A21 minus 1 raised to 2 plus 1, that is minus. Similarly, a to 2 cofactor of this 2. So again you leave the column and row in which that entry lies. Remaining entries will form 2 by 2 determinant, that is 1 3 1 3 0 5. So value is 5 and sign will be, we have to give sign plus, since a 2 2, so minus 1 raised to 2 plus 2 even power. Similarly, a 2 3 cofactor of 4. So again you leave the row and column in which that entry lies. So remaining entries will form 2 by 2 determinant 1 2 0 0. So value is 0. So we know how to find adjoint A. So for that purpose we have evaluated cofactor of each entries and using formula minus 1 raised to I plus j into mij. So A31 is 2, A32 is minus 4, A33 is 2. Now adjoint A. So first in the matrix A, each entry is replaced by their cofactor and then we will take its transpose. So rows are converted into corresponding column. So this is the adjoint A. Now according to formula, A inverse 1 upon determinant A. This is not a modulus A, this is determinant of matrix A. So its value is 1 by 10. Now in this is adjoint A, this is 1 upon determinant A. So in matrix divide each entry by 10. So finally we get inverse, A inverse equal to 1 minus 1 1 by 5, 0 1 half minus 2 by 5, 0 0 1 by 5. By same method, for practice purpose you can find the inverse of the following three matrices. First matrix is 1 0 0. Second matrix is first matrix 1 0 0 3 3 0 5 2 minus 1. So for these three matrix, using the formula, you give the name to the matrix, say A, and use formula A inverse equal to adjoint A upon determinant A, and then find out its inverse. First verify the condition for existence inverse exists if and only if determinant A should not be 0. Second example, find the inverse of matrix 1 0 0 0 cos alpha sin alpha 0 sin alpha minus cos alpha. So as usual, first we give name to the matrix. So we have suppose let A equal to matrix 1 0 0 0 cos alpha sin alpha 0 sin alpha minus cos alpha. Now first we will verify the condition of existence. For that purpose we have to find determinant A. If determinant A not equal to 0, then inverse will exist. So let us find determinant A. Determinant A 1 0 0, determinant 1 0 0, 0 cos alpha sin alpha 0 sin alpha minus cos alpha. So for matrix A we have taken its determinants, and when we evaluate its value, 1 into minus cos square alpha minus sin square alpha, you take minus common, so into bracket you will get identity cos square alpha plus sin square alpha, which is 1. So determinant A is minus 1, which is not equal to 0, and that's why inverse exists. Now again we are familiar with the formula. A inverse equal to adjoint A upon determinant A. Now first, using this formula, for given 3 by 3 matrix, we will evaluate cofactor of each entries. So now let us evaluate. So cofactor of 1. Now cofactor of 1. So to find cofactor of 1, you leave the column and row in which that entry lies. Remaining will form 2 by 2 determinant cos alpha, sin alpha, minus cos alpha. So value will be minus cos square alpha minus sin square alpha. So this is minus 1. So you can verify A11 is minus 1, cofactor of 1. Now A12. So A12 it is cofactor of 0. So to find cofactor of 0, again you leave the column and row in which that entry lies. Remaining entry will form 2 by 2 determinant 0 sin alpha, 0 minus cos alpha. This is actually minor and we will give sign M12, but this is 0. So A12 is 0. Minus 1 raised to I plus j into Mij, that is your Aij cofactor. Now, so A12 is 0. Now cofactor of A13, capital A13, cofactor of 0. So again you leave the column and row in which that entry lies. So remaining minus 1 raised to 1 plus 3 determinant 0 cos alpha, 0 sin alpha. So you can observe value of this determinant is 0. 0 into sin alpha minus 0. So A13 is 0. So first, for each 9 entries, we will evaluate their cofactors. Now cofactor of this 0. So again you leave the column and row in which that entry lies. Remaining will form 2 by 2. Remaining entry will form 2 by 2 determinant sin alpha minus cos alpha. So its value is 0. So A21 is 0. Now A22, cofactor of this cos alpha. Again we have to omit column and row in which that entry lies. Remaining determinant formed by the remaining entries 1 0 0 minus cos alpha. So value is minus cos alpha. So you can observe, and sign will be A22 minus 1 raised to 2 plus 2. It is plus, or either you give sign plus minus plus minus plus minus plus minus plus. So you can observe in entries lies in the principal diagonal and subsidiary diagonal, the entry which lies in the principal diagonal and subsidiary diagonals, minor is same as cofactor. For this entries, minor and cofactors are same. Now 823, again 823, cofactor of elements lies in the second row and third column, that is cofactor of sin alpha. Again you leave the column and row in which that entry lies. So that is 1 0 0 sin alpha. So its value is sin alpha, but it is cofactor of sin alpha, so we have to give sign. So this is minus sin alpha. So 823 is minus sin alpha. So for each 9 entries, first we have to find their cofactor. Next 831, cofactor of 0. Now cofactor of this 0. So again leave the column and row in which that entry lies. Determinant formed by the remaining entry 0 0 cos alpha sin alpha. So naturally value of this determinant will be 0. So A31 is 0. Now A32, so cofactor of sin alpha. Again we leave the column and row in which that entry lies. So 2 by 2 determinant formed by the remaining entry 1 0 0 sin alpha. So its value is sin alpha. This entry is A third row second column A32, so minus 1 raised to 3 plus 2, so power is odd, so we have to give minus sign. You can observe A32, and similarly A33 is cos alpha. So now adjoint A, first determinant formed by the cofactor of each entry minus 1 0 0 minus 1 0 0 0 minus cos alpha 0 minus cos alpha minus sin alpha 0 minus sin alpha and cos alpha. This is the matrix formed by cofactor of each entries, and then you have to take its transpose. So when you take its transpose, this is the transpose, and now by formula A inverse 1 upon determinant A into adjoint A, value of the determinant A is minus 1. So this is minus 1. Now in matrix, when we multiply it by minus 1, each 9 entry we have to multiply it by minus 1. So 1 0 0 0 cos alpha sin alpha 0 sin alpha minus cos alpha. And here interesting thing is, you can observe in this example, particular example, A inverse and A both are same. You can observe. This is A inverse, 1 0 0 0 cos alpha sin alpha 0 sin alpha, and 1 0 0 0 cos alpha sin alpha 0 sin alpha minus cos alpha. So you can verify A and A inverse are same. So there may be a question of the form, for a given matrix A, prove that A equal to A inverse. So that is one of the same. Evaluate A inverse. Next result, A and B, two matrices are given. A is given, B is given. A 3 7 2 5, B 2 by 2 matrix 6 8 7 9. Verify that A into B inverse, it is B inverse into A inverse. Now we know this is theoretical true. AB inverse is same as B inverse into A inverse. Here we have given A and B as 2 by 2 matrix, but same result you can verify for any 3 by 3 matrix. Since this result is theoretical true, so you can verify easily for 2 by 2, 3 by 3 or any square matrix. So to verify AB inverse equal to B inverse into A inverse, first we find out multiplication of A into B. Now multiplication of two matrix AB. So we know how to find this multiplication. 3 7 2 5 6 8 7 9. We know how to find this multiplication. First row, for the first matrix we have to take first row. For second matrix, using first column, prepare first column, and using second column, prepare second column. Now first row, first column, multiplication of corresponding entries, and then we have to take addition. 3 into 6 plus 7 into 7. So this is 18 plus 49. Now first second row, first column. When you prepare first column, only use first column, forget this second column. When you prepare first column, always use first column. First row, first column, multiplication of the corresponding entries, then take addition. Second row, first column. So 2 into 6 plus 5 into 7. So this 12 35. Now when you prepare second column, use second column. 8 9 now remove first column, because when you prepare second column, always use second column. So first row, second column, 3 into 8 plus 7 into 9, 2 into 8 plus 5 into 9. So this is 24, 63, 16, and 5 into 9, 45. So this is AB, multiplication of two matrices A and B. So this is AB. This is AB. Now evaluate determinant AB. So first this matrix determinant formed by this matrix 67, 87, 47, 61, and value of this determinant you can observe it is -2, not equal to 0. That's why AB inverse so AB inverse exists according to formula AB inverse. Adjoint AB upon determinant AB. This is value of determinant AB. To write adjoint AB for 2 by 2 matrix AB, it is very easy. Interchange entries lies in the principal diagonal. So 61, 67, change the sign of entry which lies in the subsidiary diagonal. So -87, -47. So you can observe this is AB inverse. Now we have to verify AB inverse equal to B inverse into A inverse. So this is AB inverse, say result number 1. Now to evaluate right hand side, B inverse into A inverse. First we will find B inverse, then we will find A inverse, and then we will find multiplication of B inverse into A inverse. Now for B inverse, first we have to check condition of existence. So for that purpose determinant B should not be 0. So this is B. So this determinant B, it is -2, which is not equal to 0. So B inverse exists because determinant B is -2, which is not 0. So B inverse exists, and by formula B inverse 1 upon determinant B into adjoint B. For 2 by 2 we have given B equal to 6879, 6879. So for adjoint B, interchange the entries lies in the principal diagonal. So 9, 6. Change the sign of entry which lies in the subsidiary diagonal. So -8, -7. So this is B inverse. Now from A, let us evaluate A inverse. For matrix A, it is 2 by 2 matrix. It determines 3, 7, 2, 5. So 5 into 3, 15 minus 14, which is 1, not equal to 0. So A inverse exists. Now for 2 by 2 inverse, easily one can obtain determinant A. 2 by 2 determinant 3, 7, 2, 5, 3, 7, 2, 5. So adjoint A, to write adjoint A, interchange the entries which lies in the principal diagonal. So 5, 3, change the sign of entry which lies in the subsidiary diagonal. So -7, -2. So this is A inverse, and since determinant A is 1, so adjoint A is same as A inverse. Now this is multiplication of B inverse into A inverse. So first this is B inverse, this is B inverse, this is A inverse, and this is multiplication of B inverse into A inverse. Again, as usual, we know how to find this multiplication using this prepare first column, using this prepare second column. So this is our multiplication B inverse into A inverse, and say result number 2. Result 1 is, this is result 1, and you can verify 1 and 2 are same. So from 1 and 2, AB inverse equal to B inverse into A inverse. And as we have discussed, since this result is theoretical true, so you can also verify for 3 by 3 matrix A and B, and AB inverse is always as B inverse into A inverse. So next time we will discuss more results.